Picture this. You have this machine flying at 10,000 feet. It is minus 40 degrees outside, and the wind is just battering it from every direction, right? It's actively trying to flip it over.
Oh, yeah. It's an environment that would instantly destroy a commercial airliner.
Exactly. And meanwhile, you've got invisible waves of electromagnetic energy from ground-based radar trying to fry its internal circuitry.
Mm-hmm.
And on top of that, fake satellite signals are bombarding it, trying to trick its navigation system into driving it straight into the side of a mountain.
Right. And through all of that chaos,
Yeah.
the machine not only survives, but it, calculates its position down to the millimeter.
Yeah, it adjusts its power output 100 times a second and just completes its mission entirely on its own. It's wild. So welcome to this deep dive. Today, we're asking you to completely discard this image you might have of drones as those, plastic, remote-controlled toys you fly around a park.
Right, the ones that just take nice photos.
Yeah, we are moving way past that. Our mission today is to go inside the hyper-complex, invisible engineering revolution that powers next-generation aerial platforms. Because, when you look at a vintage car engine, the mechanical logic is right there in front of you.
Oh, totally. You see the pistons, the belts.
The spark plugs. It's visible, it makes sense. But with modern drones, you're looking at a physical object where the reality of what keeps it in the air, the rigid aerospace standards, the algorithms, the stealth materials, it's entirely invisible.
Yeah, they're basically flying autonomous supercomputers now.
Right.
And understanding how they work really requires us to look at how they're built from the ground up, starting with this framework called the L0 to L4 layered architecture.
Layers 0 to 4.
Yeah. Think of it kind of like a biological organism, right? Layer 0 is the skeleton and the muscle. So that's the carbon fiber airframe and the actual propulsion system.
Okay, makes sense.
Then layer 1 is like the brainstem or core flight controller, making sure the machine doesn't just, fall out of the sky.
Keeping it breathing.
Exactly. Then layer 2 is the visual cortex. That's the edge computing, the AI, vision processing, what the drone is actually seeing.
Okay, so layer 3 would be, the higher level stuff?
Yeah, layer 3 is the higher level consciousness. It handles complex mission logic, threat analysis, things like that. And finally, layer 4 is the communicative mesh, the encrypted radios letting it talk to the whole swarm.
Okay, let's unpack this, because building those layers isn't just, snapping off the shelf parts together. If you want to understand how bulletproof these systems have to be, you have to look at the software standard they use, DO-178C.
Oh, man. DO-178C is brutal.
It really is. I like to think of this as the most intense forensic accounting audit in existence, but for computer code. The entire philosophy is built on one-word traceability.
Right. Every single line of code must have a documented receipt proving exactly why it exists.
Yeah, no leftover junk.
Exactly. You cannot have what they call dead code, just random leftover software from a previous version lying around.
Yeah.
Because that dead code can create unpredictable vulnerabilities.
Right. And for the most critical systems, what they call Design Assurance Level A, or DALA, like the core flight algorithms, they require something called 100% modified decision coverage, MCDC.
Which sounds like a rock band.
It totally does. But it basically means testing every single possible logical pathway. Imagine a choose-your-own-adventure book, but with a million different endings.
Yeah, the engineers have to mathematically prove that no matter which combination of if this then that decisions the software makes, it will never result in an unpredictable action.
Never. And it's not just the software, right?
No. The physical hardware gets the exact same paranoid treatment under a standard called DO-254.
DO-254.
Yeah. Modern drones rely on these complex chips called FPGAs, field programmable gate arrays. Engineers literally have to prove through intense logic verification that if the drone flies through, say, a high irradiation environment.
Like way up in atmosphere.
Right. And a rogue cosmic particle physically strikes the microchip, causing a single bit of memory to flip from a 0 to a 1. Yeah, they have to prove that tiny hardware glitch won't suddenly command the drone to dive straight into the ground.
A single radiation particle flipping a 0 to a 1, and the drone just has to know how to ignore it.
Right.
That is wild. But here's the thing, a perfectly certified lab environment is very different from that freezing, turbulent sky we talked about at the start. How does this pristine logic actually survive the chaotic real world?
Well, that transition from static design to dynamic survival happens in the guidance, navigation, and control systems, GNC.
Okay.
And the foundational rule of GNC is extreme redundancy.
Mm-hmm.
I mean, a modern high-tier flight controller doesn't just have one processor. It typically has 3 running simultaneously.
But they aren't just three identical chips, right? Because if you have three identical chips and there's some hidden math error in how that specific chip handles division.
They all crash.
Exactly. They all fail at the exact same time.
Which is why they use what's called dissimilar hardware. They use three completely different microchip architectures. So one might be an ARM processor, another might be a RISC-V processor.
They physically process the math differently.
Exactly. So if a foundational bug crashes one chip, the other two instantly recognize the error and use an independent watchdog mechanism.
Like a literal watchdog.
Yeah. It locks out the frozen chip in milliseconds and takes over the flight without missing a beat.
It's like having three co-pilots who all speak different languages but are looking at the exact same instruments.
That's a great way to put it.
And speaking of instruments, the sensors themselves are engineered for survival. Take the IMUs, the inertial measurement units.
Like the tiny gyroscopes.
Yeah, the gyroscopes and accelerometers that tell the drone if it's tilting or falling. When a drone is flying high up, the temperature obviously drops drastically, and cold actually causes the physical materials inside those tiny sensors to contract, which messes up the math.
Right.
So these IMUs are actually internally heated. They maintain this perfect constant temperature bubble, whether the drone is in a desert or like a blizzard.
And that thermal stability is what allows the drone's algorithms, specifically these complex state estimators, to juggle all that raw data and figure out exactly where the drone is in 3D space.
Without drifting.
Exactly, without drifting over time.
Wait, if GPS is everywhere, why do we need all this extra heated hardware and complex math? I mean, my phone's GPS can navigate me through a dense city perfectly fine. Can't it just follow the dot on the map?
I mean, if you're flying a toy in your backyard, sure. But GPS, or GNSS as the broader global system is called, is incredibly fragile. The signals broadcasting from space are less powerful than a standard light bulb by the time they hit the Earth.
Wow, really?
Oh, yeah. And in a contested environment, adversaries don't just jam the signal with loud noise. They use GNSS spoofing.
Digital deception.
Yes. They broadcast fake satellite signals that are slightly stronger than the real ones. They can literally trick the drone into believing it's 50 miles away from its actual location or convince it that it's suddenly upside down.
And if the drone trusts that fake GPS dot?
It will violently correct its flight path and crash itself right into the ground.
Man, so the drone has to know when the universe is lying to it.
Exactly. And when it realizes the GPS is compromised, it immediately switches to blind flying backups.
Like what?
It uses visual inertial odometry, or VIO. This is a system that uses downward-facing cameras to track the passing ground, pixel by pixel.
Oh, smart.
And it combines that with LiDAR lasers that constantly scan the terrain. But to process all this massive data in real time, the drone's internal nervous system has to be unbelievably fast.
Right. Because moving data between the flight controller and those heavy-duty AI brains, like those edge computing modules, requires a protocol called XRCE-DDS.
Yeah.
And without getting bogged down in the acronym, it basically acts as an ultra-fast, lightweight nervous system that allows massive streams of video data to flow with practically zero lag.
And that zero latency is the only thing that allows a drone to see a tree branch and dodge it in a fraction of a second.
Yeah, go.
It also has to communicate securely with the outside world, right? For ground control, they use MAV-Link version 2. It's a highly encrypted protocol that requires digital handshakes, so an enemy can't just hijack the frequency.
Right. And to prevent the skies from becoming complete chaos, there's the FAA Part 89 remote ID mandate.
Yeah, that's crucial.
It acts like a digital license plate, constantly broadcasting the drone's identity over Bluetooth or, network layers so airspace controllers can deconflict the traffic.
So we have this hyper-certified brain that thinks in milliseconds and a lightning-fast nervous system to carry the data.
But a brilliant brain is completely useless without the muscle to push it through that freezing wind. How are we powering these machines?
Well, the propulsion systems are wildly diverse, mainly because they're tailored to the exact physics of the mission. Let's look at IC internal combustion engines.
Okay.
Despite all the hype around electric vehicles, liquid hydrocarbons still hold an immense, almost unbeatable amount of energy density.
And strictly as engineering case studies here, we see this application on a lot of different platforms. Take a long-range system like the Shahed 136. It utilizes the MD-550 engine, which is a 4-cylinder boxer engine.
Right.
Now, why a boxer engine? Because the cylinders lay flat and the pistons punch outward in opposite directions. So the physical force of one piston moving left perfectly cancels out the vibration of the piston moving right.
Which is huge for drones.
Yeah. It keeps the heavy vibration from just tearing the drone's delicate electronics apart, all while pumping out 50 horsepower and flying over 2,000 kilometers.
That's incredible engineering.
Yeah.
But conversely, if you look at a tactical reconnaissance platform like the Orlan 10, it uses a hyper-efficient micro-single-cylinder four-stroke engine.
Why a four-stroke?
Well, two-stroke engines are loud and they waste unburned fuel. A four-stroke is heavier, but it burns fuel so completely and efficiently that the drone can just sip gas and loiter in the sky for up to 16 hours.
But combustion engines are hot and they are loud. If your mission requires total silence, you have to go pure electric. And the engineering behind electric propulsion has evolved way past standard motors. They use a technology called FOC, field-oriented control.
Oh, FOC is a massive leap in efficiency.
Yeah.
Because standard electronic speed controllers, they send electrical pulses to the motor in these blocky square waves.
Which causes that micro-stuttering.
Exactly, known as torque ripple. It wastes energy and creates that distinct buzzing noise.
But FOC algorithms map the magnetic field of the motor continuously, and they send out a perfectly smooth, continuous sine wave of electricity.
Eliminating the torque ripple completely.
The flight becomes unbelievably smooth and practically silent.
But pushing that much power requires intense battery chemistry. You can't just slap standard laptop batteries in there. They use specialized cylindrical cells like the Molicel series that have incredibly low internal electrical resistance.
Right.
Because think about when your smartphone is running a heavy 3D game, the back of the phone gets hot, right?
Yeah, definitely. That's internal resistance turning battery power into wasted heat. When a heavy drone suddenly maxes out its motors to fight a gust of wind, it draws massive amps. If the internal resistance is high, the battery will literally melt.
So true. Now, what happens when an engineer wants the absolute silence of an electric motor, but the massive endurance of a gas tank?
Hydrogen.
Exactly. Systems like the Raybird use a PEMFC, a specific type of hydrogen fuel cell. It chemically mixes stored hydrogen with oxygen pulled straight from the air.
No combustion.
Right. The chemical reaction generates pure electricity to drive the motors, and the only exhaust that comes out the back is water vapor.
That is so cool.
It can fly for 15 hours silently, but the engineering challenge is insane. Hydrogen molecules are the smallest in the universe. They will literally leak through solid metal.
Oh, wow.
So to carry enough of it, you have to compress it into advanced carbon fiber tanks and store it at negative 70 degrees Celsius.
And managing these advanced hybrid systems, like knowing when to pull from a battery and when to pull from a fuel cell, requires an AI-driven energy management system.
Yeah. An EMS.
Right. And the AI uses an algorithm called simulated annealing to balance the power. Imagine you're a hiker trying to find the absolute highest peak in a massive, foggy mountain range. If you just follow the simple rule of always walk upward, you might reach the top of a small hill, get stuck, and never realize there's a massive mountain right next to you.
Right. In mathematics, that's called getting trapped in a local optimum.
Exactly. Simulated annealing is a logic rule that tells the AI hiker, hey, sometimes you have to willingly walk downhill into a valley, accept a temporarily suboptimal power mix right now so you can cross over and eventually climb the true highest peak.
Oh, I love that analogy.
It mathematically guarantees that over a long flight, the drone finds the absolute most efficient mix of power, constantly adjusting for wind, altitude, and battery health.
It's brilliant optimization. But, you know, an efficient engine and a smart brain mean absolutely nothing if the physical skeleton of the drone shatters, or if its wiring acts as a beacon for enemy radar.
True.
We really need to talk about surviving the unsurvivable.
The physical testing these machines undergo is terrifying. They are subjected to the MIL STD-810H military standard. They don't just, vibrate the drone, they perform a sign-on-random vibration test.
Which is brutal.
It really is. It simulates the high-frequency rhythmic buzzing of the drone's own propellers, perfectly layered over the chaotic, random, violent shaking of atmospheric turbulence. It's like driving a car over massive potholes while the engine is simultaneously redlining.
Yeah.
And then they shock it, thermally dropping the temperature from a blistering 57 degrees Celsius down to minus 40 in a matter of seconds, just trying to force the materials to crack.
Which is exactly why traditional manufacturing is being phased out.
Yeah.
We're seeing a massive shift toward thermoplastic continuous fiber composites,
Wow.
TPCFRP.
Okay, what makes that better?
Well, traditional carbon fiber uses resins that are stiff, but they're brittle. They can snap under those thermal shocks. Thermoplastics are incredibly tough.
Yeah.
And the real advantage, you don't drill holes and use heavy metal rivets to hold the drone together.
Oh, really?
No, you literally fuse the carbon fiber pieces together using ultrasonic welding.
Wow. And they also use high-end 3D printing, right? Selective laser sintering for complex aerodynamic parts. It allows engineers to design a new wing shape, print it overnight in a nylon carbon blend, and test it the next day.
Bypassing the months it used to take to cut metal molds.
Exactly. But look, I have to ask you about the electronics inside this pristine carbon fiber shell. Because when I build a desktop PC, I just bunch all the messy cables together and zip tie them tightly into a corner.
Right, cable management.
Yeah. So aren't we over-engineering the wiring here? Why do aerospace engineers obsess over how a single tiny wire is routed? Why the strict requirement for things like star grounding and 360-degree shielding? Isn't a wire just a wire?
Not at the frequencies these drones operate at. This falls under the MIL STD 461G standard for electromagnetic interference. If you take a simple grounding wire and twist it into a little loop or a pigtail, at the connection point, the physics of electricity actually change.
Wait, what do you mean?
At high frequencies, that tiny loop of wire stops acting like a conduit for power and physically becomes a radio antenna.
Wait, really? A sloppy wire literally transforms into a transmitting antenna.
Yes, and modern drone power systems use advanced semiconductor materials like silicon carbide and gallium nitride. These materials switch huge amounts of electrical current on and off incredibly fast, millions of times a second.
Okay.
If you don't use perfect star grounding, where every single ground wire meets at one isolated central point, and if you don't encase those wires in 360-degree woven metal shielding, your own electrical system will blast out electromagnetic noise.
Meaning the drone would literally scramble its own GPS sensors.
Or much worse. That tiny unshielded wire will broadcast a glowing electromagnetic signature right to enemy electronic warfare sensors.
Giving away your exact position.
Exactly. Conversely, if an enemy fires a high-power microwave weapon at the drone, those unshielded wires will act as receiving antennas, absorbing the weapon's energy and instantly frying the drone's brain.
So a messy wire is a fatal flaw.
Completely fatal.
And physical protection from the elements is just as extreme, right? Every circuit board is covered in military-grade conformal coating. It's essentially high-tech, chemical-resistant nail polish made of specific polyurethanes.
Yeah, that's exactly what it is.
It ensures that if the drone flies through highly conductive salt fog off the ocean or magnetic dust in a desert, those microscopic pins on the microchips don't short-circuit.
So we have a machine that can survive minus 40 degrees, dodge terrain in milliseconds, and shield itself from microwaves. But true survival in a modern battle space means not being seen at all.
Which brings us to the art of disappearing. Stealth. We always think of stealth as like billion-dollar radar-absorbing fighter jets, but it's being applied to drones at the acoustic, thermal, and electromagnetic levels.
Yes.
Let's start with sound. The loudest part of a flying drone isn't actually the motor whining, it's the air violently tearing off the very tip of the spinning propeller blade, creating a pressure vortex.
Right.
So to fix this, engineers developed DSDD double-slot, double-depth propeller tips.
It's a fascinating application of fluid dynamics. They physically cut these highly precise, tiny notches into the trailing edge of the propeller blade.
And by cutting those notches, it forces the air to break up before that loud tip vortex can fully form. It cuts the physical sound output by 50%.
That's massive.
It is. But more importantly, it shifts the acoustic signature from a distinct, highly annoying mechanical buzz into a broad, soft white noise that simply blends into the ambient sound of the wind.
Right.
And the craziest part, modifying the blade this way only costs about 4% in energy efficiency.
That's a trade-off you take every time.
Oh, totally. But thermal stealth, hiding the heat of an engine from a missile. Here's where it gets really interesting.
Because modern infrared missiles are incredibly sensitive.
Wow.
I mean, if you have a hot engine or a high-discharge battery, they will find you.
So here's how they hide it. They use WSTR wavelength selective thermal regulators. The best way to visualize this is like a thermal one-way mirror. The Earth's atmosphere is weird. It blocks certain wavelengths of heat, but has these clear windows that let other wavelengths pass through perfectly. Enemy infrared missiles are programmed to look specifically through the 3 to 5 micrometer window and the 8 to 14 micrometer window.
Because that is where engine heat naturally shines the brightest.
Exactly. So the drone is painted with the WSTR coating that's engineered at the molecular level. This coating acts like a physical barrier in those exact windows. It reduces the drone's heat emission in the 3 to 5 micrometer band to almost zero.
Wow.
So the missile looks up and sees nothing but blank sky. but the drone's heat still has to go somewhere, otherwise it would cook itself from the inside out.
Right, you can't just trap the heat.
So the coating is designed to blast all of the drone's internal heat out into the 5 to 8 micrometer wavelength band.
Which is an absolute stroke of genius because the natural water vapor and carbon dioxide in the atmosphere heavily absorb the 5 to 8 micrometer band.
Yep.
So the moment the drone dumps its heat into that specific wavelength, the surrounding air instantly swallows it. It completely disperses the thermal signature before it ever reaches the enemy sensor.
A literal thermal one-way mirror.
That was smart.
And for extreme anti-jamming, where you absolutely cannot afford your radio signals to be detected or blocked, engineers are taking a radically simple approach. They stop using radios entirely.
Right.
We are seeing the massive rise of fiber optic drones. These machines carry a physical spool and literally unroll up to 20 kilometers of glass wire behind them as they fly.
It is the ultimate physical hack against the invisible war of electronic warfare. I mean, you can jam a radio wave with enough power, but you cannot jam a physical pulse of light traveling inside a glass tube.
No way.
It grants the drone 100% immunity to signal spoofing, jamming, and spectra analyzers.
When you take all of these layers, the acoustic white noise, the thermal mirrors, the dissimilar AI brains, the unjammable fiber optics, and the FOC silent motors, you start to see the culmination of tomorrow's battlefield doctrine. You get incredibly specialized avatars.
Yes, platforms engineered for very specific envelopes. You have pure electric dive bombers like the Lancet 3, using an X-wing aerodynamic design and brushless motors for a completely silent, high-speed terminal dive.
Right.
Or you have heavy-lift quadcopters like the Mammoth, utilizing those low-resistance battery cells to carry massive payloads just feet above the tree line.
But the future isn't just about building a better single drone. It's about integration, synergy. Specifically, integrating UAVs drones in the air with UGVs, unmanned ground vehicles. And this is being driven by standardization protocols like DroneCAN.
Yeah, DroneCAN allows disparate robotic systems to speak the exact same language instantly. An airborne drone can detect a threat over a ridge and seamlessly pass that targeting data to a ground robot rolling through a forest.
Without a human doing anything.
Exactly. The ground robot can act on it without a human ever bridging the communication gap.
So what does this all mean? Are humans just out of the loop entirely now?
Well, we're transitioning to a doctrine of MUMT, man-unmanned teaming. And the core philosophy of this doctrine is metal goes first.
Metal goes first.
Right. The human operators, the commanders, remain safely miles in the rear, providing high-level intent and moral authority over the mission. But the robots in the air, on the ground, on the water, they are the workforce pushing the physical frontline forward.
And what is truly wild is how fast this robotic workforce evolves. We are no longer living in a world of 10-year procurement cycles for a single aircraft. This new paradigm is powered by agile software development.
Oh, absolutely.
If an adversary suddenly develops a brand new jamming frequency on a Tuesday, engineers can analyze that battlefield data, rewrite the anti-jamming code, and push an over-the-air firmware update to thousands of deployed drones by Friday night.
They're treating physical warfare like a rapid software beta test. The carbon fiber hardware is just an empty vessel. The true weapon is the code running inside it, constantly iterating and updating.
Which brings us to the end of our deep dive today. For you listening, we've traveled from the raw physical layer of vibration-canceling engines and thermoplastic welds, up through the lightning-fast data links, and into the hyper-certified dissimilar brains of modern flight controllers.
We've seen how they mask their sound, hide their heat, and adapt to threats overnight.
Right.
They've fundamentally evolved from hardware-centric vehicles into software-defined, hyper-resilient flying networks.
But I want to leave you with a thought to mull over, building directly on this idea of software-defined weapons. If modern drones are capable of receiving massive over-the-air updates while simply sitting in a field overnight, what happens when a basic low-cost drone airframe suddenly receives an update granting it highly advanced swarm intelligence AI?
It's the ultimate modern ship of Theseus problem.
It really is. The plastic, the motors, the battery, the physical hardware you can see and touch stays exactly the same. But the capability of that object changes completely in the time it takes to download a file.
Right.
The line between a simple remote-controlled plane and a fully autonomous hunter is completely erased. How do we as a society regulate, track, or even comprehend machines that look exactly the same today as they did yesterday, but have fundamentally changed their entire brain overnight?
It completely breaks our traditional visual understanding of what a machine is capable of.
Remember what we said at the start. You look at a vintage car engine, and the mechanical logic is right there. It is visible. You can trust what your eyes are telling you. But when you look at these next-generation systems,
Yeah.
the true power, the true threat, and the true complexity are entirely invisible. Thanks for joining us on this deep dive. See you next time.